All right, so imaginary numbers. Where does it come from and why the heck do we even care about them? Well, so far in your mathematical lives, you have dealt with exclusively the real number system. But something that is not true when you deal with the real number system is that it's not possible to take a square root of a negative number. So, for example, square root of -4. Do me a favor, type that in your calculator right now. Square root of -4. What does it say? Non-real. Because the square root of -4 does not exist in the real number family. All right? It says non-real. Now, if this was you solving, so back in Math 1, when you got to this part, what were you told if you get a negative under the radical? What were you told is automatically your answer? No solution. In reality, it's no real solution. There is a solution. It's just not real. All right? So, you've learned so far that if you have this, you put no real solution. This is no longer a viable answer. Because after today, you're going to be able to calculate an imaginary answer. So, why do imaginary numbers exist? It helps us alleviate the problem of negative square roots. All right? And the reason is because there's so many things in math where if you take a negative of a radical, specifically if it's an even radical, so like square roots, fourth roots, sixth roots, if you take a negative of that, it's going to be imaginary. It's not going to be real. All right? But a lot of mathematicians, so the reason imaginary numbers became a thing way back in the day, long before even any of us existed. All right? Imaginary numbers came around because a lot of mathematicians hated the fact that they had to stop with the square root of a negative number. They wanted to see what would happen, so they create imaginary numbers so that they could kind of alleviate that issue. All right? It's more so like when you get to the really advanced math, there's more cool features that come with it. All right? So, now, and also think about it. Square root -4. If if you didn't put that in your calculator and saw that it was non-real, what would be your gut answer? -2. But what's -2 squared? +4. All right. So you would think square root of -4 would be -2. Not true. You square a negative number, that's the negative times the negative, you get a positive number. You square a positive number, positive times positive, still a positive number. There's no way to get a negative number if you square it at all. So let's look at this in terms of the actual graph. Because we know that x-intercepts, or the zeros of a parabola, help us out. Why do we care about the x-intercepts? They're the solutions. Another name for x-intercepts is solutions. So below, they have the graph of y equals x squared. Who remembers what's important about y equals x squared? We talked about this in the last unit. Abe. Well, the vertex is the origin, but I'm thinking of, it's what? It's the what? The parent function. There you go. So the important thing about x squared is that it is the parent function of the quadratic family. What does that mean? Who remembers what that means? Right. Any other quadratic is just a transformation or child of x squared. X squared is where it all begins for a quadratic. All right. So given that, we can easily figure out x squared plus 1. So given what we know about transformations, if I start at x squared and I add 1 to it, what actual transformation is going on here? It's up 1. A way you can think about it is the original vertex would be at 0, 0. Meaning if I plug in 0 for x, That would be 0 plus 1, which would give me my y. So my new vertex would be at 0, 1. So if I shift this, all you got to do is just take the normal points and just go up 1. So it would look something like this. So this would be x squared plus 1. Now, if I'm looking at x squared plus 1, what's true about the x-intercepts? There aren't any. So we have no x-intercepts. Now, at this point, again, if we were back in Math 1, if you were solving by graphing, you would say that it's no real solutions, all right, because there's no x-intercepts. This actually means there's 2 imaginary solutions. So originally, it's no real solutions, but now we can say that it's 2 imaginary solutions. Now, where does that imaginary number come from? All right, let's see if we can try solving x squared plus 1 algebraically. So if I wanted to solve this algebraically, what's my first step? Subtract the 1. I get x squared is equal to negative 1. What's my next step? Square root both sides. So x squared, or x, is equal to plus or minus the square root of negative 1. Remember, we use plus or minus because we're actually solving. This right here is where our imaginary number comes from. That is where the imaginary comes from, the square root of negative 1. And that imaginary number, we refer to it as I. Now, I write my I's in cursive when I do math for the sheer fact is I don't want to accidentally think it's a 1 or something. All right? Yes. We put plus or minus because when we're solving, you always have 2 different answers. So just like for this case, it's only one solution because the vertex is on the x-axis. But more often than not, a quadratic is going to have 2 solutions. So that's why we do plus or minus. Plus, with imaginary numbers, they always come in pairs. So, like I said, we cannot solve this using real numbers. So we cannot solve using real numbers. That's where our good friend I comes in, which is the basis of an imaginary number. Basically, an imaginary number is any set of numbers that contains an I. Have you ever noticed why we never use I as variables? Have you ever noticed that you've never seen I as a variable whenever you're doing math? That's why. Because I means something. So there's a couple of letters in the alphabet that you never use as variables. It's I, E, and honestly, that's pretty much it. I and E. Because they're both considered numbers in their own right. I is an imaginary number. E is like a very popular irrational number that you see a lot with exponentials and logarithms. That's a Math 3 concept. All right. So that's why they never use I as a variable, because it represents imaginary numbers. And all it stands for is that it is the square root of a negative real number. So the definition of the imaginary number I is that I is equal to the square root of negative 1. On the flip side, that means I squared is equal to negative 1. So funny thing with imaginary numbers is you flip-flop, depending on if you square it or cube it or whatever, you flip-flop between imaginary and real. All right, so we'll talk about that in just a minute, but it is pretty interesting to think about. So let's look at some of these. Now, simplifying radicals that are negative underneath are actually very, very easy to do, or it's actually nothing new. The only difference is is that before you can simplify the radical, we got to make it positive under the radicals. We got to make the number positive under the radical. The way we do that, we take an I out. Because if you think about it, we can rewrite this as the square root of -1 times the square root of 9, which we know the square root of -1 to be I. What's the square root of 9? 3. So this would actually be 3I. Typically, you want to write the I after the number. Now, if this was on the test and you wrote before, I wouldn't count it wrong. But just know, typically, even though I is considered a number, you write it after like you would with a variable. Yes? Say it one more time. No. Needs to be a lowercase I. So you got to use a lowercase I. Capital I means something completely different in math. It's a different symbol. So yeah, in math, cases actually do matter. It's weird, but it's just the way it is. All right, so that's kind of a way that I remember it. If the number under the radical is being negative, I want to fight it. I'm going to start by taking its I out. It's morbid, but I still remember it that way. So if the number under the radical being negative, I'm going to fight it. I'm going to start by taking its I out. Yes. Nope. We can't multiply this by -1 or divide it by -1 because if we do square root of -9 divided by -1, we can't touch this -9 because it's under the radical. All right. So this -1 can't touch it. That's why I comes into play. So all you need to know about I is if you ever see a negative under the radical, and it's already simplified to its fullest, meaning there's no other operations. You've already done all the operations, you end up with a negative number. You just got to take the I out. That'll make the number under it positive. So this one. Now, there's also a negative outside. Negatives outside of the radical are okay. Those are still real numbers. It's when they're under the radical that there's a problem. All right. So we're going to continue to keep this negative on the outside. But to handle that negative on the inside, I'm just going to go ahead and take the I out and make that a positive 100. So you don't necessarily have to write it like this. You can if you want to, just to remember, but you just got to remember that the square root of -1's I. But honestly, as long as you see that negative underneath the radical, you can just take the I out and make it positive. Yes? Because this negative was already outside, so we just have to multiply I by a -1. Which that's totally fine to do. You can multiply I to whatever number you want. But the negative was already outside of the radical. So we took care of the negative inside the radical, but the negative outside the radical is a real number. So we just bring it down. So it gets confusing because there's a lot inside outside. Inside the radical, we don't like the number to be negative. That's when we take the I out. Outside of the radical, we don't care because as long as it's outside the radical, it's considered real. All right, does that kind of make sense? Kind of, sort of, maybe? So then what's the square root of 100? So this would be -I times 10. So this would be -10I. So again, just get in the habit of writing I after the number. Because it just follows the same rule that variables do. You never see x10. You always see 10x. All right. Now, letter C, pretty much the same thing. So we start, there's a negative under the radical. We start by taking that I out so we don't even have to deal with it anymore. Now, 32 is not a perfect square. So we just simplify like normal. But our final answer is going to contain that I. Don't forget the I. Okay? So 32, what's the perfect square factor that's the biggest I can go into it? 16. So 16 times 2. So I have I times the square root of 16 times the square root of 2. What's the square root of 16? This is I times 4 times the square root of 2. Just rearrange it a little bit. 4I square root 2. Yes. Yeah. Try letter D on your own. And keep in mind there is a negative on the outside. So the number that you have on the outside is going to be negative at the end. Because yes, negative I does in fact exist. Nope. Can't. Even though we're multiplying by a negative on the outside, can't touch that negative on the inside with the radical blocking it. Yeah, but the negative one's on the outside. The negative one's under the radical. So square root of negative 1, the negative is under the radical. Just like there was a negative outside of the radical. Let's get it wrong.
It's like literally just something that you can concentrate. We get to the point where we got mad.
So guys, this is the easy side of imaginary numbers. When we start solving with quadratic formula, you will run into those solutions.
Question: in the real world, will I ever use imaginary numbers?
Oh, yes, you are. If you do anything in math, you're going to talk about imaginary numbers.
But like, when I'm like the real world,
You may not. They're mostly used in engineering, but you know what? So that I pass this class, so that I pass high school, so that I pass that math pre-EOC, and you will see imaginary numbers in that. So, yeah, you have to learn them.
some random dude just said I.
Imaginary numbers actually do come into play with your voting stuff as well.
What would it say math again? What would it math?
A lot of people, so Pythagoras, Euler, I hope they all just they're locked in.
No, if I ever get a time machine though, I'm going back and get a bunch of
But math also makes the world go round. It's the basis of physics, which is
we don't even know this. We don't
We
need
don't need to know physics. It's already in place. Like, you don't
Yeah,
need
an
to
object in motion stays in motion, right?
again.
This conversation is not at the tip of class.
Yeah, if you don't touch an object, it's gonna keep going. Like,
I felt the same.
If an apple falls,
yeah, like,
Look, all I'm saying, guys, is the reason you gotta know this, it's gonna be on the test. Another reason you gotta know this, you're gonna need to pass this class. Another reason you gotta know this, you're gonna need to pass math 3. So if you want to graduate high school, which these 2 classes you have to pass, you gotta know it.
I failed
It's
foundation.
not resolved which graduate from Penn State.
wait, what?
Not kidding.
I was just paragraph.
Just women, yeah. But then it was
I failed foundation.
So last year.
Yeah.
all right, let's go over this. All right, so negative 18. First thing you do, take that I out. And we're going to keep it negative on the outside because there's already a negative right here. So the 18 becomes positive underneath once we remove the I. Now, when you simplify the 18, what are the two factors of 18 where one is perfect square? 9 and 2. This would be negative I times the square root of 9 times the square root of 2. So this would be negative 3I square root 2. Any questions? So that's simplifying with I. Again, that part specifically, you're going to see a lot, especially when we get to solving by completing the square, solving by taking a square root, and solving with quadratic formula. All right. Speaking of, let's talk about it. Here's some solving by taking a square root. How do I solve this? First step. Subtract 8 to both sides. I get 5x squared is equal to negative 20. Next, divide by 5. We got to get that x squared by itself. Do not take a square root until that x squared is by itself. Even if the number being multiplied to it's a perfect square, don't do it. So, x squared is equal to negative 4. Square root both sides. X is equal to plus or minus what? 2i. Now, since we're solving, we got to invoke the plus or minus. All right, if we were just simplifying, you don't really need plus or minus. But solving, yes, you do. So that's kind of how you know if you need to use plus or minus or not. If you're simplifying, so you're not solving for a variable or anything, you don't have to do plus minus. If you are solving, you have to do plus minus. At least when you're doing radicals. All right, let's try this one. First step, subtract 20. I get 1/2 x squared is equal to negative 18. Then what do? Multiply by 2. Why would I multiply by 2? It's the same thing as dividing by 1/2, or we just have to multiply this fraction by its, what's the word? Reciprocal. So if you flip 1/2, it's 2 over 1, which is just 2. So I multiply both sides by 2. Cancels out the 1/2. X squared is equal to negative 36. Now I can take my square roots. X is equal to what? Plus or minus 6i. All right. Last one. Walk me through it. What do I need to do? Add 10. I get 2x squared is equal to negative 26. Then what do? Divide both sides by 2. I get x squared is equal to negative 13. Take my square roots. X is equal to what? Not 13i. Plus or minus I square root 13. All you had to do is take the I out. 13 is a prime number, so you can't simplify it further. So, guys, do not write the I under the radical. It does not go there. Yes. That one? Yes. Nope. So, this is why we do plus or minus when we solve. So, let's just say let's just do an easy one. Let's say I just had x squared minus 4 equals 0. Let's just solve it by taking a square root. So, what would be the first thing I do? Add over both sides. I get x squared is equal to 4. Take a square root of both sides. X, if we just did the positive, would be equal to 2. However, if you graph this function in Desmos, how many x-intercepts would you get? 2. What would they be? Negative and positive. So that's why we put the plus minus. because we don't know for sure whether they are meaning the plus, the positive version, or the negative version. All right, so in this case, we're accounting for both. So the same thing applies for I. I almost always comes from here to plus minus. But the I. Yeah, when we're solving, you shouldn't really get a negative outside the square root to solve. So that won't really come into play for solving it. The only time you see a negative outside the square root is if you're simplifying. So if you're simplifying, you just keep the negative as 20 plus minus anyway. If you're solving, you're forward like this. All right, now. So this next one, let's think about this logically. They want us to evaluate 5i times 6i. Think about this carefully. 5 and 6 we can multiply like normal. What's 5 times 6? 30. Now, I times I. So we got 30 times I times I. What's another way I could rewrite that? 30 times I squared. Well, don't we know what I squared is? It's negative 1. So this would be 30 times negative 1, which is just negative 30. So it wouldn't be 30i, it would be negative 30. So that's kind of a weird phenomenon that happens with imaginary numbers. When you square them, it automatically becomes a real number again. When you cube it, it goes back to imaginary. When you fourth it, back to real, and so on and so forth. So if you raise I to an even power, it becomes a real number. If you raise I to an odd power, it stays imaginary. We're about to talk about what answers you'll typically get. So, with the power of I, we have a remarkable pattern. So simplifying large powers of I, it's going to be one of 4 cases. So let's look at this. We already know that I the first power is I. And we already know I the second power is what? Negative 1. Well, take a guess. What do you think I to the third power is? Negative I. Why negative I? Right, because if we rewrite I cubed, we can rewrite this as I squared times I. I squared is negative 1, and then I to the first is just I, so negative I. All right, what about I to the fourth? Positive 1. Because we can rewrite this as I squared times I squared. So that's negative 1 times negative 1, which is just 1. So, in reality, these are the 4 cases that will happen. Your answer to whenever you raise I to a power is either going to be I, negative 1, negative I, or positive 1. All right. So, I the fifth. How I say this to do this is find the closest multiple of 4, because what you're going to discover is that multiples of 4 are always going to be 1. All right. So, if I do I the fifth, we already know that I to the fourth is 1. Well, how many i's do I have left over? 1. So I have, and I the first, just I. So I the fifth is equal to what? Just I. I the sixth, again, we know I the fourth is 1. How many i's do I have left over? 2. So I have I squared, which is equal to what? Negative 1. So what's 1 times negative 1? Negative 1. You guys seeing the pattern here? So I the fourth We know that's 1. How many i's do we have left over if we're doing I to the 7th? 3. And what's I cubed? Negative I. And what's 1 times negative I? Negative I. Lastly, I to the 8th. Right, it's I to the 4th times I to the 4th, because there's 4 left over. So that's 1 times 1, which is just 1. So here's kind of the pattern. So when you're simplifying powers of I to the first is always I squared is always negative 1, I cubed is always negative I. And then I to the n power is 1 if n is a multiple of 4. What does it mean to be a multiple of 4? Right, you can divide, 4 can be divided into it evenly. So you can divide by 4 evenly. Now, whenever you're trying to figure out, so here's kind of my rule for whenever you try to figure out what it is. What I tell my students is find the lowest multiple of 4. Find the closest multiple of 4 to the power and make sure it's lower than that number. Then figure out how many you have left, and then that will give you your answer. So what I mean by that, look at I to the 38th. What is the closest multiple of 4 to 38? 36. So I have I to the 36, which we know since that's a multiple of 4, it's going to be 1. Now, if I have 36 i's, how many do I have left over? 2. So what's I squared? Negative 1. So what's I to the 38th power? Negative 1, because 1 times negative 1 is negative 1. Here's the other way you can figure it out. If you can't figure out the closest multiple of 4, because sometimes the numbers get high, you can always, in your calculator, divide 38 by 4. If you do that, I believe you get like 9.5. You then take that number that's in front of the decimal place, multiply 4 back to it, and that'll give you the closest multiple of 4 to your answer. All right? Does everyone understand what I meant by that? So divide the original exponent by 4, take whatever number is in front of the decimal place. So if it's a 9, a 10, whatever, multiply that by 4, and that gives you the closest multiple of 4 to that number that's less than it. And then just figure out how many i's you have remaining. You can also do it that way. That works too. But some people, they just don't think like that, so that's the other way you can do it. So, I the 21st. What do you think the closest multiple of 4 is? 20. And again, make sure those multiples are less than that exponent, because sometimes the closer multiple of 4 is actually the bigger one. You want the smaller multiple. Yes, sir. On this test, yes. Times. How many i's do I have left over? 1. So based off of that assumption, we have 1 times I. So what is I to the 21st equal to? I. What about 83? What's the closest? 80. So I the 80th. How many do I have left over? 3. So this will be 1 times what? Negative I. So what's my answer? Negative I. Now, it's always nice when your exponent actually is a multiple of 4, because if it's a multiple of 4, your answer is automatically 1. 40 can easily be divided by 4. You get 10. So answer, I don't even have to do anything. It's automatically 1. Now, Colin, to answer your questions, where does this come into play? Look at the next problem. Now we got to evaluate some expressions. So, evaluating these expressions will actually give us a complex number, which is a mixture of a real and an imaginary number. So first off, my recommendation, figure out what I to each power is before you do anything. So I to the 16th, I to the 23rd, I to the 26th. What do you guys think I to the 16th is? It's 1. 16 is a multiple of 4. What about 23? It's negative I. Closest multiple of 4 is 20. And then you have 3 left over. What about 26? So what do you think I to the 26 is? Negative 1. Closest multiple of 4 is 24. You have 2 left over. Now I'm going to take these values and replace them for each of their counterparts respectively. So I have 5 times 1, which is I to the 16th, plus 3 times negative I, plus negative 1. Do a little simplifying. This will be 5 minus 3I minus 1. Now, when it comes to adding and subtracting numbers, you can only subtract real from real, imaginary from imaginary. All right? Yes. Say it again. Do what again? Oh, like do the whole problem again? Yeah. So, I to the 16th, that's a multiple of 4, so it's automatically 1. You divide 16 by 4, you get a number. That's nice. I to the 23rd, the nearest multiple of 4 is 20. So that's 1. Then you have 3 left. You got 3 left over. So that would be I cubed is negative I. 1 times negative I, negative I. I to the 26, nearest multiple of 4 is 24. So that'll be 1 times, you have 2 left over, which is I squared. I squared is negative 1. So 1 times negative 1 is negative 1. And then I just replace them. Does that make sense? All right. So now, I can only combine, it's almost like combining like terms. I can only combine real with real, imaginary with imaginary. All right. And the reason that we can't just automatically do that up here is because adding exponents, you can't do that. All right. It's only when you multiply them. But let's say you had 3i minus 4i. That would just be negative I. All right. So as long as I is not raised to anything, you can combine. But if I is raised to something, that's when you have to evaluate it. So 5 minus 1 is 4 minus 3i, and we leave it at that. So this is actually a true complex number. A complex number is made up of 2 parts. It's made up of a real number, and it's either added or subtracted to an imaginary number. So it's a real number plus or minus an imaginary number. That's what a complex number is. And typically, the real number goes first. All right, so typically the real number goes first. So the answer would be 2. All right, any questions on imaginary numbers, evaluating them, finding its powers, anything like that? All right, your homework for tonight is going to be pages 11. What's the next page? 9 and 10. So your homework for tonight is pages 9 and 10. Say it one more time. Most likely, yes. So 9 and 10. Yeah, I'm gonna check it tomorrow because I gotta check my other classes tomorrow. And honestly, you could probably knock it out before class ends because you got like a solid 35 minutes. Yes. The what? Huh? What's blocked? because I've pretty much blocked everything but math stuff. The reason I do that is I had students in the past that abuse that and try to just not do work and play it, so I do hardball. That's why.